Hey guys, Dr. Brown here, and tonight we have a unique integral. We have the integral of the cube root of x divided by the square root of x plus the fourth root of x, all integrated on x. Now I'm off the screen here, so bear with me. You don't need to see me. And I'll apologize for the messy board, but I have spinal stenosis, so it's a struggle for me to stand up for any length of time. And then secondly, I didn't know if I could get all of this correct in one take, so which that might have been the bigger issue. Okay, so bear with me. All right, let's take and change the cube root to x to the 1/3, the square root x to the 1/2, plus x to the 1/4. That's the fourth root of x. Now you'll notice we have a 2, 4, and a 3. So my least common multiple or least common denominator of that would be 12. So I'm going to take x to the 1/12 and set it equal to u. Now if I raise both sides to the 12th power, x to the 1/12 raised to the 12th is x to the 1st, and that equals u to the 12th. Now if I take the derivative of this, bring the 12 down, 12, and then that's 12 times u to the 12 minus 1, or u to the 11th, du, and that equals dx. Well, since I have x equals u to the 12th, I can raise x to the 1/3 power, and that's u to the 12th raised to the 1/3 power, which is u to the 4th. Okay, x to the, if I raise it to the 1/2, that's u to the 12th raised to the 1/2. That's u to the 6th, and then x to the 1/4 is u cubed. So now, if I take that u information and say plug it all in here, so x to the 1/3, that's u to the 4th, and then du was 12u to the, dx was 12u to the 11th du, and then square root of x was u to the 6th plus x to the 1/4, which is u cubed. Okay, so take the 12 to the outside, u to the 4th times u to the 11th is u to the 15th. Factor a u cubed out of this denominator, so that gives me u cubed times the parentheses of u cubed plus 1. And then if I divide the u 15 minus, divided by u cubed, that's 15 minus 3 is 12. So 12 times the integral of u to the 12th, u cubed plus 1, du. I'm going to take that up here. Whew. Okay, now partial fraction time. And how do I know that? Well, you know our tools. It's long division time. Partial fractions are coming. But our tools, U sub, Trig sub, integration by parts, so UTI, PP, LCQ. U sub, Trig sub, integration by parts, partial fractions, power reduction, long division. Okay, long division. What's a candidate for long division? When I have a numerator, power in the numerator, that's equal to or greater than the power in the denominator, that's a candidate for long division. So, having said that, long division just separates this thing out and makes it very manageable. So, u to the 12th divided by u cubed plus 1, and you guys know how to do long division, but that ends up giving me u to the 9th minus u to the 6th plus u cubed minus 1 plus 1 over u cubed plus 1. And that works perfect to take this piece of it, still 12 times that integral, and I separated it into that plus 12 times the integral of 1 over u cubed plus 1 du. So integrating this side, increase the power by 1 and then divide by that. So I end up with 12 times the parentheses of 1 u to the 10th over 10 minus u to the 7th over 7 plus u to the 4th over 4 minus 1 plus, still have this integral I need to work with, 12 times the integral of 1 divided by u cubed plus 1. Now you'll notice at this point in time that is the sum of two cubes. U cubed plus 1 cubed. Hey, 1 cubed is 1. So I can take and separate that out into u plus 1 times u squared minus u plus 1. That would give me u cubed plus 1 if I FOIL that out. Okay. Now that is a candidate for partial fractions. So let's take that guy and go up here. And again, sorry for the sloppiness. So 12 over, which was 12 times this 1, 12 over this, u cubed plus 1, which we've changed it into the sum of two cubes. That equals a over u plus 1 plus bu plus c over u squared minus u plus 1 du. So doing some algebraic manipulation, I multiply both sides by u plus 1, u squared minus 1 plus 1. Well, that cancels the u plus 1 here, so I end up with a times this other term. And then if I do that again, it cancels out this term, the u squared minus 1 plus 1. And it leaves me with bu plus c times parentheses of u plus 1. Now when you look at this, you're trying to solve for a and b and c, obviously. Well, if I let u equal -1, it wipes out that other side. So let's do that. So I end up with 12, -1 squared is 1, minus a minus 1 is plus 1 plus 1, so it ends up with 3a, and all of this is gone on the other side. 12 equals 3a, so a equals 4. Now if I let u equal 0, this is 0, that's 0, so I end up with 1 times c, which is c, and 0, 0, and 1, so 1 times a plus c equals 12. Well, we said a was 4, so 12 minus 4 equals c, so c equals 8. Now if I go through this again, let u equal 1, I end up solving for b, and it's -4. So now I have a, b, and c. A is 4, b is -4, c is 8. So now I can plug in the blanks here back into this equation here. So a over u plus 1 du plus the integral of -4 plus, that's b, and plus 8, which was c, over u squared minus u plus 1. This piece is easy. That's 4 times natural log of u plus 1. Oh, and by the way, I've been circling the piece that's solved. At least it's in the u world, and we'll have to take it back to the x world later. So here's another piece of the equation. So now I'm working with this other side. So I have -4u plus 8 over this u squared minus u plus 1 du, and this should have a du right there. All right, so now I'm going to let t equal u squared minus u plus 1. So dt is, if I take the derivative of that, it's 2u minus 1 du. So dt over 2u minus 1 equals du. And I should have a du right there. Okay. All right, so I have this integral now, -4u plus 8 over t, which was this u squared minus u plus 1. And then du is replaced by dt divided by 2u minus 1. Well, now I have another opportunity for long division. I'm going to, at least my thinking was, if I take minus 4u plus 8 and divide it by 2u minus 1, I can separate that into two pieces. Keep in mind it's still divided by t and integrated on dt. So if I make that division, I end up with minus 2 plus 6 over 2u minus 1. And I've separated those out here. So now I have the integral of negative 2 dt over t. So that's negative 2 natural log t, which is negative 2 natural log of u squared minus u plus 1. But I still have this other piece over here, plus the integral of 6 dt over 2u minus 1t. Now, it was at this point that I decided, why don't I just walk back to the u world, because dt over 2u minus 1 is du. So I can go back to letting this equal du. So it's 6 du over t, and t was this term here. So I end up with integral of 6 du over u squared minus u plus 1. And the reason I did that was because that to me was a candidate, I thought, for completing the square. So if you look at the b term in that, it's negative 1. So that's negative 1 over 2 squared equals 1/4. So to make this completing the square, I add a 4th here, and I subtract a 4th there, from that 1. So that gives me u minus 1/2 squared plus, and this would be 3/4. Well, if I want to square that, I'd have to take the square root of 3 squared would be 3. 2 squared would be 4. So if I take the square root of 3 over 2 squared, now I have what I need. So a squared was 3/4. Oh, by the way, this looks like tangent. So I have something squared plus a, and I'm letting a be square root of 3 over 2. So let's let u minus 1/2 equal a tangent theta. So now we're getting into trig sub. So du, take the derivative of both sides, equals a secant squared theta d theta. So let's plug in the blanks here. Du was a secant squared theta d theta. 6 stays on the outside. This was a tangent theta, but it's squared, so that's a squared tangent squared theta minus a, which is square root 3 over 2 squared. Factor out the a squared, that gives me tangent squared minus 1. Well, that is secant theta. So the secant squared, that's tangent squared theta. That's a plus, by the way. Okay, I think that was the only mistake I had there. All right, tangent squared theta plus 1 is secant squared, so those cancel. A divided by a squared gives me 1 over a. So I end up with 6 over a, the integral of d theta, which is 6 over, and a was square root 3 over 2 theta, and theta would be, where is it? Yeah, tangent inverse of u minus 1/2 over a. So tangent inverse of u minus 1/2 over a. Okay, so that's 6 divided by a, and a square root of 3 over 2. Invert and multiply, I have 12 over square root 3. Invert, multiply this one, multiply the 2 through. So that's 2 times u minus 1/2 gives me 2u minus 1 over square root 3. If I get the square root of 3 out of the radical there, or out of the denominator, I end up with 4 square root 3 tangent inverse 2u minus 1 over square root 3. Now, that's my other piece. So I have 4 pieces here. This one, that one, this one, and this one. You know, they're all added, subtracted, whatever their signs are together. So if I put that together, I end up with 12 times u to the 10th over 10 minus u to the 7th over 7 plus u to the 4th over 4 minus u plus 4 natural log u plus 1 minus 2 natural log u squared minus u plus 1 plus 4 square root 3 times tangent inverse of 2u minus 1 over square root 3. However, that's not in the x world, that's the u world. So we've got to take u to the 10th over 10, for example. U to the 10th. Let's take, here we go. All right, u, if I raise it to the 10th power, I'm raising x to the 1/12 to the 10th power. So I have x to the 10 over 12, which would be 5 over 6. So 12 times x to the 5 raised to the 5 over 6 power divided by 10. Now u to the 7th. If I raise this to the 7th power, that's x to the 7 over 12. And I go through that process all the way down, and that gives me plus x to the 1/3 over 4 minus x to the 1/12 plus 4 natural log of u, which was x to the 1/12 plus 1 minus 2 u squared. So I have x, u squared would be x to the 2 over 12, which is x to the 1/6 minus x to the 1/12 plus 1 plus 4 square root 3 tangent inverse 2x to the 1/12 minus 1 over square root 3 plus c. That's a long problem. It takes a long time just to talk about it, and it's already written out. So I would encourage you, when you just sit down and go through this thing, you've got u subs, long division, partial fractions, another long division here, multiple logarithmic items in there, and then you're going to trig sub, and then once you get your answer, now you're taking it back from the u world, actually from the theta world to the u world back to the x world. So it's a good problem. Challenges you in many ways, and obviously it challenged my organizational skills, which I didn't do very well. Okay. Why are we doing this? Together we're trying to build a better tomorrow. How? We're trying to build that better tomorrow through math. Keep studying, studying, studying. I can't overemphasize that. Keep working problems. You'll get better. You'll trip and fall, but even if you fall forward, hey, that's still progress, okay? All right, that's all for now, and we'll talk to you next time. Thanks.